All right, so this is our last set of notes. This is covering bounce collisions or elastic collisions, right? Easy car bounces back. Yeah. So welcome back. This is our last set of notes in the momentum unit, and this is covering bounce collisions or elastic collisions. In this type of collision, our our objects bounce off of each other and do not stick. Now the difference here, because this is the same sort of definition as we had before for inelastic collisions, right? Two objects just bounce. Perfectly inelastic, meaning that they stick together. For an inelastic collision, they don't always have to stick. That's just perfectly inelastic. Now, elastic collisions, they don't stick together, but they also keep all of their kinetic energy. So no energy lost. No energy is lost from the interaction. All right. And just a note on kinetic energy, you may remember that its formula is 1/2 mv squared, 1/2 times the mass times the velocity squared of the object. And we can just rewrite this as 1/2 mv times v, right? These two things are the same. And oh, look at that. This looks a lot like momentum. 1/2 p times v. Well, let's also do something else. I can rewrite 1/2 p squared over m, because p squared over m is just m squared v squared over m. And we're left with mv squared. It's all the same. So kinetic energy can also be rewritten as our momentum squared over 2 times the mass. It's kind of fun. Right, and up here, our kinetic energy is equal in both before and after. So let's do an example with a elastic collision. We have a 2 kilogram cart moving at a speed of 0.5 meters per second on a frictionless track, and that means that there's no outside forces. And it hits a motionless, excuse the roughness of this drawing, 3 kilograms motionless cart, and then our 2 kilogram cart bounces back at 0.1 meters per second. Just call that negative. And then we want to know what is this velocity after the collision. Right, this is before and after. So we can always use conservation momentum just because there's no outside forces being applied to our system. So we can just do some quick multiplication here. 2 times 0.5 is 1 kilogram meters per second. And obviously, momentum of this cart is 0 because it's not moving. So this is our initial momentum. Our initial is equal to our final, which is equal to our 2 kilogram cart. Now moving backwards at 0.1 meters per second, plus 3 kilogram cart moving with some unknown speed. And let's see, this is all equal to 1, by the way. That was our initial momentum of the system. We can multiply together with 0.2. I'm just going to add that over to the other side and go 3 kilograms times our V final equal to 1.2 kilograms meters per second. We can divide by our kilograms, or 3 kilograms, and noticing our units work out, which is good. Our final velocity is going to be 0.4 meters per second, and it's positive, which is also good because we know that our car is moving to the right.